Okay, so we're ready to begin Chem 113, Experiment 8A, which is a transesterification reaction under acid catalyzed conditions, where we are synthesizing ethyl laurate from ethanol and lauric acid. So, what's interesting about this reaction is that it is catalyzed by an in situ generated equivalent of hydrochloric acid. This is generated from the added acetyl chloride. So, to begin, we are going to dispense into our 3 milliliter conical vial with a stir bar. We are going to dispense our ethyl laurate, our acetyl chloride. We'll dispense our lauric acid, our acetyl chloride, and our alcohol, which in this case is ethanol. And then we're going to heat the reaction mixture for approximately 1 hour in order to force the reaction to completion. So we'll allow the reaction to proceed at a gentle reflux at a bath temperature of around 110 degrees Celsius. As our acetyl chloride catalyst is sensitive to moisture, we have prepared a water-jacketed condenser with a calcium chloride drying tube. So our first step is we're going to add our reagents, which are the lauric acid and the ethanol, as well as the acetyl chloride catalyst. We'll then assemble the setup and begin heating our reaction mixture while circulating water through our water-cooled condenser to minimize losses of material. So we'll resume once we've added all of our reagents into our conical vial. So we finished out weighing our reactant lauric acid. So I'd like you to record the mass of lauric acid that we will use in this reaction for experiment 8A. We're going to add this to our conical vial, and then we'll add our ethanol solvent and reactant, and then we'll add our acetyl chloride catalyst to generate the trace amount of hydrochloric acid in situ. So we'll resume once we've added all of our reagents into our conical vial. Okay, so we've assembled our setup and we've mixed our reagents. What we're now going to do is we're going to install and clamp down our conical vial into our heating block. Our heating block is still in the process of warming to the target temperature. So we're trying to heat to a bath temperature of about 120. So in the meantime, what we're going to do is we're going to get our cooling system and cooling bath set up, and we'll resume once we've reached the target temperature. The heating bath and the heating block takes a fairly long time to reach the target temperature, so I'm just showing you the completed assembled setup, and then I'm going to add the water circulating water condenser. So we'll resume once we've reached the target temperature and we can begin timing the reaction. Okay, so we have our chilled water condenser set up. We only turn the condenser on once our entire setup has been prepared because the condenser encourages the condensation of water, and we do not want water condensing into our reaction flask and quenching our catalyst. So we're still waiting for it to reach the target temperature, and once it reaches the target temperature, we'll begin timing the reaction. So after a little bit of waiting, we've reached the target temperature for our bath temperature of 120 degrees Celsius. So we're then going to heat our reaction mixture to allow this transesterification reaction to proceed. We're going to heat this reaction mixture for 1 hour at a gentle reflux. So we'll resume once we've finished heating this reaction mixture for the required 1 hour reaction time. So as it's been 1 hour and our reaction has gone to completion, what we are going to do is we are going to allow our reaction mixture to cool to room temperature. So we're going to raise our reaction mixture out of the heating bath and we're going to allow our reaction mixture to cool to room temperature. So we'll resume once the reaction mixture has cooled to room temperature, and we can begin the next step of our procedure, which is concentration of our reaction mixture. Okay, so our product mixture has cooled to room temperature, and now what we're going to do is we're going to concentrate this reaction mixture to remove as much of the ethanol as possible in a sand bath under heating. So we're going to transfer our reaction mixture and our reaction mixture vial to a sand bath, and we'll evaporate off the solvent under a stream of nitrogen. Okay, so we've transferred our reaction mixture to a sand bath, and we're going to evaporate off the excess ethanol solvent at 80 degrees Celsius under nitrogen. And we'll resume once we've completely evaporated off the majority of our solvent. We're concentrating to a final volume of about 0.25 milliliters before we do the resulting quench and extraction. Okay, so we've concentrated down our reaction mixture. So now what we're going to do is we're going to add diethyl ether, and then we're going to add sodium bicarbonate, and we're going to rinse the ether layer repeatedly with sodium bicarbonate. So to facilitate this process, we're first going to remove the stir bar. Okay, so we've removed our stir bar. We're then going to add the ether, and we're going to resume when we start the quench with sodium hydrogen carbonate. Okay, so we've now added some extra diethyl ether to dissolve our product. And now what we are going to do is we are going to sequentially rinse our product mixture with 0.25 milliliter aliquots of 5% sodium bicarbonate. So we're going to add our first aliquot using a calibrated pipette. And make sure to add the aliquot dropwise because the mixture will bubble. Okay, so we've added our water layer. Okay, so we've added our aliquot of sodium hydrogen carbonate. And now what we're going to do, we're going to take our mixture and we're going to cap our mixture and mix it using a vortex mixer. So we'll resume after we finish this mixing process in a vortex mixer. So we've mixed our aliquots in a vortex mixer, and now what we're going to do is we're going to wait for the layers to settle, and then what we're going to do is we're going to carefully remove the aqueous layer. And remember, because we're in ether, the aqueous layer is on the bottom. That is a mistake you really don't want to make. Okay, so we're going to carefully remove the aqueous layer. And we're going to save the aqueous layer in a separate container. Okay, so now what we're going to do is we're going to repeat this process, and we're going to rinse 3 times, 3 additional times. So we'll do our second rinse now. And again, we'll bring this rinse into, we'll mix our sodium hydrogen carbonate and our reaction solution in ether using a vortex mixer. So we're going to carefully vent our reaction mixture, and then we're going to carefully remove the aqueous layer. Okay, so we'll continue on with this rinsing process with 2 more rinses, and we'll resume after this rinsing process is complete for the 4th time. So we'll add another aliquot. We're going to mix with a vortex mixer, so this is our 3rd rinse. One interesting thing to note is you can clearly smell the characteristic smell of acetic acid in your reaction mixture, especially in your aqueous layer. And that makes sense because the acetic anhydride is being hydrolyzed to yield acetic acid and eventually sodium acetate. Okay, so let's remove our aqueous layer once again. That time it was a little hard to see on the camera, but I had to view it a little bit up close. Okay, so we'll resume after we completed our 4th and final rinse. Okay, so again, please record the mass of this conical vial that we'll be using to concentrate our column fractions and collect our purified product. Okay, so we have our product mixture in diethyl ether that we've rinsed repeatedly. And now what we're going to do is we're going to purify our product via column chromatography. So we have our column prepared that has sodium sulfate, 500 milligrams on top, and 500 milligrams of silica gel on the bottom. We have our previously weighed and tared 5 milliliter conical vial containing a boiling stone. So now what we're going to do is we are going to begin to elute our product mixture through the column, and then we'll collect the column fractions in our 5 milliliter conical vial. So in our first step, we're just going to wet and rinse the column with 0.5 milliliters of dichloromethane. So we're allowing 0.5 milliliters of dichloromethane to completely pass through our column and in turn wet the silica gel. It's important that you allow your solvent to fully elute. Okay, so now what we're going to do is we're going to load our product mixture. So we have our product mixture, and we're going to load it onto our column. This is why we concentrated our product mixture. Because if we have too much of it, if we have too much solvent, we're not going to get good resolution when we run the plug. Okay, so we're going to allow our product mixture, that initial aliquot, to run through the column. And now what we're going to do is we're going to rinse our original flask with a 0.5 milliliter aliquot of dichloromethane. So we have our original vial, and we're going to rinse it with 0.5 milliliters of dichloromethane. Now we're going to add that mixture again to our column. And we're going to allow our product mixture to continue to elute. We're going to repeat this rinsing process for a total of 2 total times. So we'll do another rinse with another 0.5 milliliter aliquot. So we have our crude reaction flask, we're going to collect our product mixture, and then we're going to load it onto our column. We're going to allow this portion to elute through the column, and then we're going to rinse and allow an additional 1 milliliter of dichloromethane to elute through our column. Okay, so as our initial portion has eluted effectively through the column, we're going to add another milliliter of dichloromethane to ensure all of our product has been successfully eluted through our column. And again, we're collecting our product mixture in our tared conical vial. So we'll resume once this elution has fully completed. Okay, so we've now isolated our product. So now what we're going to do is we're going to concentrate this volume down in a sand bath under a stream of nitrogen. Okay, so we're concentrating our product mixture down in a sand bath under a stream of nitrogen. And we'll resume once our product has been completely isolated and this methylene chloride has been completely removed. Okay, so we've finished concentrating our product, and now we're going to weigh our product on the balance, and then we're going to do some chemical tests. Okay, I would like you to record the mass of our isolated ethyl ester product. And you can use this isolated mass calculation in conjunction with the empty reaction flask mass to calculate the yield for this esterification reaction. We're now going to move on, and we're going to take an IR, and we're also going to take a proton NMR of our product. We're also going to perform a series of chemical tests, and the IR, NMR, and chemical test observations will be provided on Canvas. Okay, so let's take a liquid film IR spectra, So we have our two salt plates. We have our product mixture. And now what we're going to do is we're just going to deposit our sample onto the plate. Okay, perfect. So we're now all ready. We're going to compress our sample between the two plates, and we're going to record the IR spectra for our product, ethyl ester. Okay, so we're going to do some solubility tests now. So what we're going to do is we're going to take a small volume of our product. And you know what's really funny is that the product has a very characteristic smell. Unfortunately, you can't observe through a recording what something smells like. Nonetheless, we're going to transfer our material into a test tube. And for our first test, what we're going to do is we're going to try to dissolve our material in a small amount of water. So I'm going to add another small aliquot. Okay, and this is going to require give me one moment to clamp this so that way you can visualize what's going on. So this is what our water product mixture looks like. So here's our water product mixture, and although it's a little hard to see on the camera, I'm going to explain verbally. When you try and mix your product, ethyl laurate and water, what you observe is that the ethyl laurate remains undissolved on top of our water layer. So let me try and do a zoom in of this. Okay, so as we can see from the top, there's a clear heterogeneous separation between our ethyl laurate layer and the water layer. Okay, so we're now going to observe the solubility of our product ethyl laurate in sulfuric acid or phosphoric acid. So let's add some of our product. So we initially have our product in our test tube. And now what we're going to do is we're going to add a small volume of sulfuric acid. I'll be narrating the observations because we're dealing with such a small volume and it's hard to pick up on the camera. So I'm going to add the sulfuric acid and then we'll discuss our observations. So upon mixing our ethyl laurate with sulfuric acid, we observe a yellow homogeneous solution. So I'd like you to record your observations. And next, we're going to look at the solubility of our ethyl laurate in phosphoric acid. So again, we're going to prepare So we prepared a solution, and we've prepared an aliquot of our product mixture. And now what we're going to do is we're going to add a small volume of concentrated phosphoric acid and record our observations. So as we can see, when we add a solution of concentrated phosphoric acid to our ethyl laurate sample, the ethyl laurate dissolves and we get a homogeneous solution. From these observations and the provided data in this recording and on Canvas, you have all the information you need to complete this laboratory.